Hello everyone, my name is Junaid, and the screen you see represents respiration. There is this entire process of respiration. In this part is aerobic respiration, and then we have this small part which shows anaerobic respiration. So let's start talking about the aerobic respiration over here. Aerobic respiration starts with glycolysis, then go on to a link reaction, and then there is this Krebs cycle, and finally we have electron transport chain and oxidative phosphorylation. This is considered as one process together. We have this glycolysis take place in the cytoplasm, as it can be seen here, and then we have Krebs cycle and link reaction in the matrix, and then in this region, the region between the membranes, which is the intermembranous area, in this region we have electron transport chain take place. So in the membrane of the mitochondria, this is mitochondria. In the membrane of the mitochondria we have this electron transport chain taking place. Now we know that raw material for respiration are oxygen and glucose. So here we can see glucose, starting with, let's start with glucose. The glucose enters here. Another name for glucose can be hexose, which simply means 6 carbon. The first thing happens is it gets phosphorylated. So here the ATP, one of the phosphate from the ATP gets attaches to hexose, and it becomes hexose phosphate, and then another one, this changes to ADP. Do not forget that this ATP changes to ADP, and hexose biphosphate, hexose phosphate becomes hexose biphosphate. It is all have 6 carbon. We change this in this form. Instead of just breaking down glucose, we change it to hexose biphosphate, then we break down to triose. This is because the activation energy of glucose is very high compared to activation energy of breaking down hexose biphosphate into 2. That's why we change it to this form, so it becomes easier for us to break this down. So here we break this down to form 2 molecules of triose phosphate. Remember that this is triose, so triose means 3C. Then from these 2 molecules of triose we come to form an intermediate, after which we get these 2 molecules of pyruvate. Now triose phosphate and pyruvate, there is not much difference. There is just hydrogen are released, and this phosphate, which you can see over here, is released. So there are 2 molecules. We get 2 ATP, and then we get another 2 ATPs here. So the next ATP for glycolysis will be 2, and there will be 2 NAD from these. What are these NADs? If we want to figure out, they are just carrier proteins. They are these carriers of energy, something we can call it like that. They get hydrogenated, means they gain hydrogen, which later on break down in this final stage, which is the electron transport chain. It breaks down over here to give us to give us energy, to give us ATP. Okay, so this part is essential for the final stage. Okay, hope that is understood. Now let us come to this so the glycolysis starts with glucose and ends up with pyruvate. We have triose phosphate in between. It breaks down, then it changes to pyruvate, which is also 3C like triose phosphate. And then we enter with the pyruvate in the link reaction. In the link reaction, the pyruvate hydrogenize NAD to the reduced NAD, and decarboxylation takes place, so carbon dioxide is removed. So we know that pyruvate is 3C. If 1 carbon is removed, it will become 2C. So this acetyl 2C, this simply is acetyl coenzyme. Maybe this will be a little confusing. You can remove this and keep it over here. This means acetyl coenzyme with 2C. Okay, so from pyruvate in the link reaction we get acetyl coenzyme. Okay, so this is the final product for link reaction, and we get a reduced NAD and we get a carbon dioxide, one molecule. Then, so if we investigate here from this both, we get ATPs and we get reduced NADs, and we say that these reduced NADs are very important. These are the ones that goes to the final stage of electron transport chain to give us this so-called a lot of ATPs. Okay, so we enter in the cycle. Now this cycle, it looks this scary kind, then it looks like complicated, but it's not complicated. We have here we have citrate. Sorry, I didn't write that before. So that's citrate here. We have citrate, which is the 6C, and so this acetyl coenzyme releases its coenzyme and becomes citrate, which is also 6C. This is 2C. Okay, so where does it get 4C? It gets 4C from here, because this 4C oxaloacetate plus acetyl coenzyme, after coenzyme is removed, it becomes citrate. Citrate is 6C, this is 4C, 4 plus 2 is 6. Hope this clear. So what happens is this compound acetyl coenzyme gets here, it becomes 6C, then it gets decarboxylate, it reduces NAD, and then it releases carbon dioxide, again it reduces NAD, and then it forms ATP, and then there is FAD. Now remember that this FAD and NAD, they are similar, they have the same function. NAD gets reduced the similar way, and FAD gets reduced. Okay, the only difference is in their molecular structure, which we don't require to know. So 5C will become 4C after losing carbon. So remember, this carbon is lost from this carbon, and then we get 4C. And so this goes on, and we have this oxaloacetate, which is 4C, and this cycle goes on. Now in Krebs cycle, the only essential thing is the reduced NADs and FADs. These are the ones that enter the next cycle, which we really require. Then we continue the cycle with this electron transport chain. Over here you can see this there is a small structure which is very essential. Actually, we have to get this very clearly. This all the NADs which were here, I mean in the Krebs cycle, and from the glycolysis, all pile up over here, and we have them all here. Then that reduced NAD gets back to NAD, the normal NAD. Okay, we can see here it gets back to NAD, and it releases hydrogen, H positive. No, it releases H, which is hydrogen. Okay, so maybe we can write the equation here, so it becomes clearer. Hydrogen, okay, which gives us hydrogen positive and gives us electron. Okay, so that's what we get. That's what we get from this reduced NAD. I mean, from this one we get this one. Okay, hope that's clear. Then this one specifically, this one comes gets here. This is the hydrogen carrier, and this one is the electron carrier. So these two, hydrogen carrier and electron carrier, we see here hydrogen carrier and this is electron carrier. They move to a lower potential energy. So where does these potential energy that they lose go? And the answer is it goes to form ATP from ADP. We know that if we break down ATP to ADP, we get energy. And if we want to make ADP become ATP, we need energy. So where does this energy come? This energy comes from the energy which is lost in hydrogen carriers and hydrogen carriers and electron carriers to move to a lower potential energy. So this is where the energy comes from to form this. So this circle simply shows that the energy is coming from somewhere else, and from ADP we get ATP. Hope that's clear. And then the final thing is the hydrogen that comes down here gets oxidized again with the electron, and it reacts with the oxygen. Oxygen, we said there are two raw materials. We say we mentioned that there is this glucose, which is used in glycolysis over here, and then there is oxygen, which is used over here in the electron transport chain. So that's very clear. That should be very clear now, that this oxygen reacts with hydrogen, which comes down here, which again forms hydrogen H. This one, I mean, this reaction is reversible. This reaction is reversible. So this comes back to this, and we get hydrogen, and hydrogen reacts with oxygen to give us water. Hope that's clear. And oxidative phosphorylation simply means there is a phosphorylation, there is formation of ATP, and oxidation means there is oxygen reacting with hydrogen to form water. So that's clear. This part is clear, hopefully. And then the last part is this one, the anaerobic part. This one is very simple. We have this glucose. It either goes on to form pyruvate, as we know, like in glycolysis. But then there is 2 ATP formed over here, and NAD, 2 NAD. The same procedure of glycolysis, like this. Okay, there are 2 ATP net and 2 NAD. Okay, look. But then this is ethanol pathway. This is lactate pathway, because there is lactate here and there is ethanol here. Okay, so in the ethanol, there is this aldehyde formed, from which after carbon dioxide is being released. Means this pyruvate loses its carbon dioxide and it forms aldehyde, which then forms ethanol. Okay, but in lactate pathway, which is in animal, this does not happen that way. I mean, this glucose, after forming pyruvate, directly goes on to form lactate. So it's like a direct process. So this one is more faster, and lactate is poisonous, so it does form back the other. It forms some other compounds. Okay, it gets oxidized and all that. So hopefully that's clear, and please like the video if it was any useful to you, and you can subscribe my page, and you can comment below. Thank you.